slides here. All right, so we're down to chapter 2, which is more C programming. And I should be able to get that. Which takes me a minute to get to the right folder. And there it is. Should be, there it is, opening up somewhere. All right. All right. So more C, and of course we're using the same free online textbook. Do I do any online class Twitch streams for 121? I'm not teaching 121, but I do have, I do answer any questions people bring me. And if you go to my old classes, they have the lectures from last semester when I taught it. But I'm not teaching it this semester as another teacher, Richard Wu. Good. Anyway, so here's what we're going to talk about. More information about how C handles variables, and in particular, probably the most important thing is pointers. Pointers are what get people pretty confused. Yeah, good. All right. So, all right. So you have local and global variables. Here you have the start of a C program, including a library. Then you have a couple variables defined up here before you define any main or any other functions. Those are global variables. These are function prototypes. Will be defined later. Here's a global variable, int gx. So this will be available. Its scope is the entire program. However, the things you define inside main, like int x and result, these are local, so they're only going to exist within this scope. From the opening curly brace to the closing curly brace, they'll only exist while this function is running. That's the scope of a variable in C. So you can have a max function that declares a local variable named val, and you can have a change function that defines a local variable named val, and even though these names are the same, they're completely separate variables and they won't collide or anything, because this is the val that exists only in this scope, and this is the val that exists only in that scope. All right. So you got the local variables reside on the stack. Each time you call a subroutine, it adds another stack frame here to have enough room to store the local variables and a few other things. And then that function calls another subroutine that will make another stack frame. And when that function returns, it will restore to the previous stack frame, and the data left above will just be leftover data that will get written over later in future function calls. So pointers are real important in C, and this is one of the really big things about C. If you have a variable, say this integer variable has 10. Okay, that means there's a location which is called var, which contains the value 10. Now it has to be somewhere, and if it's on the stack, it's probably at an address like this. So you'll have a stack address to it, and ampersand var. This is going to be, p is going to be a pointer. You define int star p, and p is going to be the pointer to it. So p is going to be the address of var. So p is a pointer that stores the address, and the data type of p and var should match in the sense that it's a star p is an integer. So the star is the dereference operator that will look this up. So star p means take p as an address and look up the value there. Ampersand var means take the variable var, and the ampersand means find the address of that and put it in p. So people get really confused about this learning C, but it's thing to know. Star p and ampersand are the things to learn here. And manipulating pointers is very powerful in C, and therefore also in assembler, but it's easy to get confused and foul it up. So you can declare a pointer variable. This is int star pointer, so the thing pointed to by ptr is an integer. Ptr points to an integer. Here cptr points to a character. So you can initialize it. You can set it equal to the address of x with an ampersand. That's one way to do it. All right, you can use null. Null is an invalid address. So you should never dereference a null. If you try to look up something at null, you're going to get an access exception. It's an invalid address. That's the point. If they're null, they go nowhere. You dereference a pointer variable with the star. So pointer is the address of x, and star pointer is 8. So dereferencing is taking this reference and finding the data stored at that reference. All right. So here you've got x equals 8. Pointer is the address of x, and pointer 1 is null. So pointer 1 points nowhere. You got two pointers here. Pointer 1 is null, not leading anywhere. Pointer 2 is the address of x pointing to x where you have the data 8 stored. All right. And so here's the memory location. Pointer 2, that's an integer variable. It contains 10, and y is going to be 10 plus 3. Pointer 1 equals pointer 2. That's going to make the pointers point to the same variable. So now if you change the value stored in pointer 1, it's going to also affect the value stored in pointer 2. So this is useful if you want to pass variables to a subroutine and have that subroutine modify the variables in the calling program. You can do it by passing pointers. So here you got one of the variables changed, and therefore that changes the value of both of them. Now you can set pointer 1 equal to the address of y. That's going to move it from pointing here to pointing down here. Now you can store data in there, and it won't affect the data stored in x. All right, so this will assign a pointer to address 20. You're going to put this value in the pointer, and that's going to lead to an invalid address when you try to use it, because 20 is not a valid memory address reserved for the use of your program. The low memories like that are generally reserved for the use of the kernel, not for any userland program. And here's star pointer is 20. This is correct. You take the integer value pointed to by the pointer and set a value in there. So if you dereference a program that doesn't have a valid address, it will crash. So here the pointer is null. So when I try to put 6 in that location, it's going to crash because I'm not allowed to go to null as an address. And here it's going to crash because although 20 is an address, it's not an address that can be reserved for use by a userland program. Here, I'm going to set pointer equal to some arbitrary value x, which is almost certainly not going to be a valid memory address. It'll probably crash. In principle, if x actually has a value that points to memory reserved for your process, this might survive, but the odds are against it. This is what you probably intended. The pointer would be the address of the variable x, and then you store it in 6. Like I say, that's why you get in trouble when you start using the ampersand and the star. Little mistakes will cause crashes. So you can test for null pointers. If the pointer is not equal to null, then set it equal to 6. This is a good practice. All right, so let's take a look at a Kahoot. I should have them ready to go here. 2A is here. All right, good. All right. Okay, so what part of memory contains local variables? They go on the stack. All right. Okay, what part of memory contains global variables? They go in the data section. The heap is where temporary variables assigned with alloc would go, malloc, and the code is the executable machine code. So the data section, that's where global variables go. All right, how do you dereference the pointer PTR? Star pointer will get you the data stored at the address that pointer points to. That's dereferencing it. Okay. All right, good. All right, so pointers and functions, and I mentioned before, this is one of the places you get some value out of them. So here I've got a function that will double a number. Here's the double number, and so it's going to take a pointer. The argument is a pointer to val. So when I set star val2 times val, it's going to change it and then return 0. And so when I run this, I'm going to call double of a pointer to the number. So since I passed the subroutine a pointer, when it changes this value, it's changing the variable in the calling routine by address. So now before double number it's 5, after double number it's going to be 10. This is how you can define functions. By the way, I was just helping my students doing the embedded device capture the flag contest last night, and they have some sample code, and the sample code is written like this. So all the variables reside in the main routine, and all the functions have pointers, and on an ARM processor, that makes it essentially impossible to exploit buffer overflows. So that's kind of one reason you might do it this way. Of course, a more common way to do it would be to return double the value, and then up here you would say value equals double number. That's often what you do, is return the value, where you calculate it with a local variable and then return it, but you can do it this way, where your function actually works on the actual value stored above it by passing a pointer. Normally, arguments pass by value, so it makes a local copy. So here's an example of that. Here you just pass the value, double number. So now if you pass it the value 5, it's going to make a local copy of 5, make a local variable called 5, double it, but when it returns, it's not going to change this number. So before it's 5 and after it's still 5. This is when you normally pass an argument. The value of the argument is copied into a new local variable, and it's not affecting the calling routine. All right, so you can pass a pointer variable, so you get to change the argument value. All right. And so the same thing you've got here. If you're going to change the value, I passed star input. And so down here, I change star input to 100 or change it to something else. And so that means that it is going to change up here. When I call change value, I pass the pointer to x, and this function is going to change x. All right, so here they are showing you your original main x is 100. I pass the address in here. And so the change value subroutine is still using the x up there, so it will change it. All right. All right, and now we can talk about dynamic allocation. So you can have a pointer on the stack that points to memory allocated on the heap. You do it with malloc. Malloc is what reserves some room on the stack. So you do malloc and then tell it how much you want to reserve. Typically use the size of, so you know I may allocate enough space to store an int. Now this is p. I can now use p as I might want to do it, but p is going to be a pointer to the malloc, and star p is going to store an integer. All right. So malloc might fail. There might not be enough free heap memory, so you might check to see if it's null. Then you'll have a null pointer, and you should know you ran out of memory. A good programmer would do error handling rather than just letting your program crash. So when you no longer need the memory, you should call free. So you allocate it with malloc and you free it with free, and then in best practice is to also set the pointer to null so you don't have what's called a dangling pointer, where this pointer can be used and it's going to change values on the heap that are no longer allocated for this purpose, and you might be able to exploit that. You might be able to take over the box with it or change some value that the developer did not want you to change. And if you call free twice, you can create a condition where data is overwritten on the heap, and again, lose control of the box. So you can have dynamically allocated integers and dynamically allocated strings. This is going to save enough room to store 20 integers. This is going to save enough room to store 10 characters on the heap. And if, of course, as always, if you are in main and you have an address in the heap, you can pass that to a subroutine, and then it will be able to change the value in a subroutine just like it did do in the first one, if you pass a pointer down there. All right, let's try another Kahoot. I got 2B here. All right. All right. All right, so which function will be able to modify the value of x in the calling program? Yep, the yellow one. You have to pass in a pointer to x, which means the dereferenced x is the integer you're changing, and this is actually changing data in the calling program. All right. All right, when malloc fails, what happens? It returns a null pointer. All right. All right. What causes dangling pointer errors? Yep, failure to call free. You malloc stuff and then you forget to free it, so you have a ref variable which is pointing to memory that might be being reused for a different purpose. All right. All right. All right. So, all right, then you have arrays. We've already used them a bit. So you can define 30 floating point variables, enough for 20 characters, and so on with the square brackets. It starts counting at 0. So if you want to access the array elements, you go from 0 to 10, and you can calculate this average is going to be a floating variable, 0 plus I, and then you can set name sub I is A plus I. Now this is the kind of horrible stuff that you'd only do in C. A is going to be the 61 in hexadecimal, 6 times 16 plus 1, the ASCII value of the letter A, and this adding 1 to it is going to make it a B, and adding 2 to it is going to make it a C, and so on. That's a sort of horrible thing. Characters are integers in C. All right, and so here name, the 10th item is going to be a null byte, storing a string. So this is one common thing. If you have an array that's 20 characters long, you cannot store a 20-character string in there. You can only store a 19-character string. You have to have an extra byte at the end for the null byte. This leads to a lot of problems. People often don't put in the null byte, or they overwrite the null byte, or forget to allow room for it, and it fouls up their strings. So here it's going to print the averages sub 3, name sub 3, and name. The averages sub 3 is going to be 3. Name 3 is going to be D because it's A plus 3, which is B, C, D. And name is going to be the whole string, name, which is going to be A, B, C, D, E, F, G, H, I, J, all these 10 characters. So that's what it's going to do here. It's going to copy hello into name. So it's going to take this long string and replace it by just hello. And after the hello, this is going to write 6 bytes into it. The 5 characters in hello followed by the null byte is going to go in there. And that's why the stir copy function is one of the dangerous ones, which copies one string into another without knowing how big this one is. So you can copy one that's too big into an array that doesn't have enough room and have a buffer overflow. So you can dynamically allocate these arrays. You can call malloc to dynamically allocate them, and then you can use them just as before. The only difference is they're stored on the heap, so when you're done with them, you really ought to free them and set them to null. All right, and so this is going to be an array of 6 integers, each of which is typically 4 bytes, although they might be a different size on some systems. And here's an array of 4 characters, each of which is 1 byte. So you have, here's arrays and elements. So if you look at the address, if you have an array storing integers, then it'll go up by 4 bytes each time. IArray1 is stored at this address, IArray2 at that address, and so on. But character arrays will be 1 byte per character. All right. So constants are easier to read than literal values. So if you have something that you might want to change, you could define n and then refer to n all over the place, n being like the size of some calculation you're doing, and maybe you want to make it bigger later. So there's a handy thing to do. Define a constant, and it will be filled in by the compiler, which we'll talk about later. So it's just like you literally typed it in everywhere, but it's just going to be easier to update in case you want to change it later. And you can have 2-dimensional arrays, 3 in this dimension and 4 in that dimension. So it's going to store them in this order, with the second parameter changing first. This is going to be important when we get to efficiency of your code. If you put them in this order, they'll be correct and easy for the program to read out of RAM. If you were to refer them by indexing this array first, it would slow down your program because it would keep having to jump by large jumps here and keep doing repeated read operations instead of being able to do one big read operation to load many values at once. They'd both work. One would just run slower. All right, and then you got strings, the big problem of C. You can have statically allocated strings. Here I have a string with 10 bytes. Here I put the first character to H, next one to I, next one to null. That's going to make the string high. Here I'm going to copy string 1 into string 2. So string 2 better have enough room to store the full length of string 1. In this case, that's fine. String 1 is only 3 bytes big, and the string 2 has 10 characters, so it'll work. That's how it works. All right. There's going to copy each of the printable characters in string 1, followed by the null byte, into string 2. So these are the dangerous functions: stir copy, stir cat, and so on. The fundamental problem with them is there's no parameter determining the length. They just expect the programmer to know what the length is, and often they don't. Which is, even if you know about this, you think about how programs are actually developed. One developer writes it, they leave the company. Years later, some other developer updates it to add new functions. Years later, this whole function is reused in some other environment for some other purpose, and pretty soon people have forgotten how long that string is and that it might run off the end. Just like pretty soon people have forgotten, you allocate the variable somewhere and you free it somewhere else, and then somebody doesn't call that other function, so it never gets freed, or somebody calls that function twice. That's how these problems that seem like it would be easy to avoid, they're not easy to avoid in the real world of software development, where what you're doing passes through many hands, or even through the same developer's hands, but a year later. They say, add another feature to this thing, and you no longer remember all the little details of how you did it. So, strcpy is the safer version. This is like strcpy, but it includes a length. So it's easy to explicitly say only copy this many bytes, and therefore it's more likely for you to pay attention to how many bytes you're copying and only copy the right number of bytes. It's still possible to copy too many or to forget about the null byte, but it's less likely that you will forget. And so here I do strcpy of hello there into string. That's going to make 11 bytes for the length. It doesn't count the null byte in the ling that's calculated with strlen. Here I'm going to allocate length plus 1, and then I can do a strncopy of string into dstr. This is only going to copy the first 5 characters, and then I'll have to explicitly add the null to the end. So that will give me hello. All right. So strlcopy is a new one, which will only copy up to the first null byte or size -1. It automatically chooses the length so as to never overflow. This is a really good idea, but it's not present in all versions of C. This would be a lot better. This is actually adding to C something which has never been there, is actually checking to see if you're overflowing and make sure you don't overflow the way all modern languages like Python and Java would. All right, then you got string comparison and string end comparison. You can't compare the characters in the strings. It will only compare the base addresses. If you compare S1 to S2, you'll just be checking the address. If you actually want to compare the strings, you got to use this function, strcompare. And you can do strcompare. This will compare them byte by byte, and this will compare this many characters of it to decide if 2 strings are equal. So here's strcopy example. I got alligator and zebra. I'm going to copy alligator into string and zebra into dstring, and then compare them. And so if ret equals 0, they're equal. Otherwise, 1 is less than 1. Alligator is less than, actually, I think alligator is greater than zebra, because a lowercase a is bigger than a capital Z. Yep, that's what I thought. This is why it can drive you nuts. It's not English alphabetics where Z would come after A. It's ASCII, where capital letters start at 41, so in hex 65, and lowercase letters start at 61. 6 times 16 plus 1, I think 97. Anyway, that's why the idea of whether one string is bigger than another, you have to understand the ASCII values. All right, and here we're going to do string cat, which will just copy this string into there, append characters in this to the end of this. So it's going to add this to the end of that and put a null byte at the end. And this is going to copy the first so many characters into there. Cat, combining 2 strings to make a longer string. And again, the destination might be too long to fit in the reserved space. Here you can locate a substring inside a string, and here you can locate a character inside a string. These are search functions that are useful. And then sprintf will print to a string instead of printing to a printer or a file. You sprintf into a string, and once again, if the string is not long enough, you can overrun. And so you've also got functions for individual character values, like is lowercase, is uppercase, is alphanumeric, is digit, and so on. These, I've never used any of these, but I guess you could if you're doing a lot of character handling. And here's convert strings to other types. This will convert a string to an integer, and this will convert a string to a float. And what I mean there is that the string is a string like this, 4.56. It'll take that and evaluate it as the floating point, 4.56. That's the A to F, and here's 1, 2, 3, 4. So that's how you do this function, where you're going to have people typing in a number, and you're going to want to interpret it as a number, even though it comes in as a string. All right, let's try another Kahoot. right. Okay, how many bytes does it take to store A after that declaration? Ten bytes. A character is a single byte integer in C. All right, how many bytes does it normally take to store A after this declaration? A is int of 10. "40. Integers are usually 4 bytes long in C. All right, which function here is the safest to use? Yes, dir n copy is safer because it will remind the programmer to pay attention to how many characters you're copying and fill in that value n with hopefully a good value, whereas these others will automatically, that should be str copy, these others will automatically read the length of the second parameter and the programmer might not realize that it's too long. All right. All right.